Good morning, students. Today we will be solving some problems related to ray optics or geometrical optics. Only those problems in which you ask me doubts will be solved here. So let us see problem number 6.10. Refractive indices of water and glass are respectively 1.3 and 1.5. If the focal length of a convex lens in air is 20 centimeter, then what is its focal length in water? This is the question. So here, in order to solve this question, we will have to use the lens maker's formula. If you don't know the lens maker's formula, in the description I have given the link to the video that explains that. You can watch it, or you can directly come here and understand the lens maker's formula and use it. So let us try to solve the problem. So what are the quantities given? Refractive indices of water and glass. So refractive index of water is 1.3. So let me express this as mu water is equal to 1.3. Here refractive index of water means refractive index of water with respect to air or vacuum, and the refractive index of glass is 1.5. So that is mu g is equal to 1.5. If the focal length of a convex lens in air, so the focal length of convex lens in air is given as 20 centimeter. What is the focal length in water? So if we keep the lens in water, what will be the focal length? So focal length of the lens in water is what? This is the question. So from lens maker's equation, we can tell that 1 by focal length is equal to refractive index of the lens or the glass divided by refractive index of the medium minus 1 times 1 by R1 minus 1 by R2, where R1 and R2 are the radius of curvature of the two sides of the lens. So here, let us take the first case when the lens is kept in air. So here, the focal length is given. So instead of F, I am substituting FA. So I have 1 by FA is equal to, when the lens is kept in air, I can use the refractive index of the lens as the refractive index of glass, absolute refractive index. So here, refractive index of glass divided by, now the medium is air. So I have to take the refractive index of air. What is the refractive index of air? 1. So 1 minus 1 times 1 by R1 minus 1 by R2. So let me substitute the values here. I have 1 by FA. FA is given as 20 centimeter. So 1 by 20 is equal to mu g. Mu g is equal to 1.5. So 1.5 by 1. So no need to write. So 1.5 minus 1 times 1 by R1 minus 1 by R2. Or I can write it as 1 by 20 is equal to 1.5 minus 1 is 0.5 times 1 by R1 minus 1 by R2. This I will take as equation number 1. Now let us take the other case. What is the focal length if the lens is kept in water? So here I am going to use the same lens maker's formula, but here instead of FA I will be using FW, that is the focal length of the lens in water is equal to, instead of mu L, I can use refractive index of glass because the lens is made of glass. So mu G divided by, here the medium is water. So I have to use the refractive index of water, which is mu W. So mu W minus 1 times 1 by R1 minus 1 by R2. So here 1 by FW is equal to refractive index of glass is 1.5 divided by refractive index of water is 1.3 minus 1 into 1 by R1 minus 1 by R2. Here, in order to remove the fraction part or the minus part, let me put 1 as 1.1 divided by 1.1. So I am writing 1 here as 1.3 divided by 1.3. So the denominator became same. So I can write this as equal to 1.5 minus 1.3 is 0.2 divided by 1.3 times 1 by R1 minus 1 by R2. So I have 1 by FW as this quantity. So here I mark it as equation 2. Now we have got equation 1 and equation 2, and there is where if we divide these two, 1 by R1 minus 1 by R2 will get cancelled. So there will be only one unknown quantity, which will be FW. So let us try doing that. What I am going to do is, I am going to divide equation 1 with equation 2. So let me do that here. I am going to rub these equations. We will not need that. So equation 1 divided by equation 2. So that will give us, equation 1 is 1 by 20 divided by 1 by FW is equal to, here 0.5 divided by 0.2 by 1.5, and this will get cancelled. So here it's divided by a fraction. So I can take the reciprocal and multiply to it. So it will become FW divided by 20 is equal to, here again I can take the reciprocal. So 0.5 times 1.3 divided by 0.2. Or if I take 20 to the other side, I can get FW. So FW is equal to 0.5 times 1.3 times 20 divided by 0.2. You can use your calculator at this point, and I got the result here as 65 centimeter. So this is the focal length of the lens when it is kept in water. So focal length of the lens when it kept in water is 65 centimeters. So what happens to the focal length of the lens when it is taken from air to water? Will it increase or decrease? It will increase. So that's the focal length of the lens in water. Let's see the next question. Question number 6.21. Jemima was working with a glass convex lens in air whose radii of curvature are respectively 15 cm and 30 cm. And the refractive index of glass with respect to air is equal to 3/2, and the refractive index of water with respect to air is equal to 4/3. So when you tell refractive index of glass with respect to air, it's nothing but the absolute refractive index of glass, and refractive index of water with respect to air means it's the absolute refractive index of water. Now find the focal length of the lens. This you can do using the lens maker's formula, but here they have given the radii of curvature, and we have to consider the sign convention for radii of curvature. If you have any confusion regarding the sign convention, the class dealing with that, its link is given in the description below. You can check it out, or you can see here how we solve that. So the refractive index or the radii of curvature are respectively 15 centimeter and 30 centimeter. So here we have a convex lens. Suppose this is surface 1 and this is surface 2. We know that a convex lens is formed by two spherical surfaces. So each surface will have a radius of curvature. So this surface is part of a circle like this, and if this is the center of the circle and the radius of curvature of the first surface will be here. So this will be R1, and suppose this is the second surface, so it will be part of another circle and it has a center here, suppose, then this will be R2. Now, according to sign convention, the radius of curvature is considered positive if it is measured in the side where the light goes after refraction. So, if we have an object here and the light is incident here, then what happens? It will go, and after refraction it will go in this direction. So, R1 is measured in this direction, here on this side. So, we can take R1 as positive. But R2, is it on the side where the light goes after refraction? No, it's on the other side. So, R2 we will have to consider as negative. So, let me consider the radii of curvature of two surfaces of the convex lens. R1 will be considered as positive and R2 will be considered as negative. So let me rub this part. I hope this is clear to you. And if you have any doubt regarding that sign convention, see the class. So I have R1 is equal to 15 centimeter and R2 I am taking it as negative is equal to minus 30 centimeter. Now for A, we want to find the focal length of the lens. So if they just say the focal length of the lens, we assume that the lens is kept in air. So using the lens maker's formula, which we used in the previous question also, we have 1 by Fa. I am taking here A because we suppose that the convex lens is kept in air, is equal to refractive index of the lens, which is made of glass, divided by the refractive index of the medium, which is air here. Air has a refractive index 1, minus 1 times 1 by R1 minus 1 by R2. So here this is equal to refractive index of glass with respect to air is given as 3 by 2. So I can write it as 3 by 2 divided by 1, no need to write, minus. Instead of 1, in order to make the denominator same, let me write it as 2 by 2. 2 by 2 is 1. Into 1 by R1 is 15 centimeter and R2 is minus 30. So minus 1 by minus 30 centimeter. So 1 by Fa is equal to 3 by 2 minus 3 by 2 will give you 1 by 2. So 1 by 2 times, I have here minus and minus. So this will become plus. So let me write it as 1 by 50 plus 1 by 30. Or in order to make the denominator same, I can multiply 2 in the numerator and denominator here. So this will become equal to 1 by 2 times 2 by 30. What I have done is multiplied the numerator and denominator with 2. So 2 by 30 plus 1 by 30. So this is equal to 1 by 2 times 2 by 30 plus 1 by 30 will be 3 by 30, which is equal to 1 by 10. So this is equal to 1 by 20. So 1 by Fa is equal to 1 by 20. So what will be Fa? Fa will be equal to 20. And it's in centimeters because the radii of curvature are given in centimeters. So the focal length of the lens, we have found it out, it is 20 centimeter. So here we got the answer. What is the answer? Focal length of the lens is equal to 20 centimeter. Let us now solve the B part. If the lens is immersed into water, then whether its power will change or not. How can we find the power if we know the focal length? Power is equal to 1 by F, but note here the focal length should be mentioned in meters when we find the power in diopters. So I'll be converting the focal length into meters and using it in this problem. So let me rub the A part. For B, if the lens is immersed into water, so before going for power, we have to find the focal length. We know that when the lens is kept in water, the focal length will change, and we can find out that focal length using the lens maker's equation. So I have here 1 by F. Now it's in water, so FW is equal to, then refractive index of the lens, that is glass, divided by refractive index of the medium, which is water, minus 1 times 1 by R1 minus 1 by R2. So this is equal to refractive index of glass is given here. Refractive index of glass with respect to air, that is 3 by 2. So 3 by 2 divided by refractive index of water with respect to air, that is 4 by 2. So instead of divided by 4 by 2, I am multiplying with its reverse or reciprocal. So times 3 by 4 minus 1 times 1 by R1. We saw while solving part A that R1 is positive, so it is 15, 1 by 15, and R2 is negative, so it is minus 30. So here we get it as equal to 3 times 3, 9, divided by 2 times 4, 8, minus, here again 1 I am writing as 8 by 8 in order to make the denominators same so that it is easy to solve the fractions. Then here you may be remembering the value of 1 by 15 plus 1 by 30. We solved that while solving part A. What was that? It came as 1 by 10. So 1 by 10. If you have any doubt, just rewind a little bit and see this. So this is equal to 1 by FW is equal to 1 by 8 times 1 by 10. So this is equal to 1 by 80. So 1 by FW is 1 by 80. What does that mean? FW is equal to 80. Will it be meters or centimeters? Here we have used the radius of curvatures which are in meters. So we will have to here centimeters. So we will have to use here centimeter. So we got the focal length of the convex lens when it is in air is 20 centimeter, which is equal to 0.2 meters. And again, the focal length of the lens when it is immersed in water is equal to 80 centimeters, which is equal to 0.8 meter. Now, let us go forward and find the power in each case. PA represents the power of the lens when it is kept in air. So, power of lens PA is equal to 1 by FA represented in meters. So, 1 by 0.2 which is equal to 5. D for diopters, that is the unit of power of a lens. So, power when it is kept in water is 1 by FW, which is equal to 1 by 0.8, which is equal to 1.25. You can use your calculator if you have one now. So, what happened to the power? Is it remaining the same? No, it decreases. So, the power of the lens decreases when we immerse it in water. So, here we find that the focal length of the lens will increase if we keep the lens in water, while the power of the lens will decrease because the power is related to the reciprocal of the focal length. So, the power will decrease when it is immersed in water. So, I hope that the solution is clear to you. Let's go and see Here we have the next question. A convex lens of refractive index 1.5 has radii of curvature respectively 0.2 meters and 0.3 meters. Refractive index of glass with respect to air is 3/2 and that of water is 4/3. Find the focal length of the lens in air. Will there be any variation of focal length in water? Analyze mathematically. This is a similar question, but here they have given the refractive indices and also the radii of curvatures, and radii of curvature are represented in meters. I always prefer to use centimeters while solving such problems, because when it comes to the reciprocal and numbers with decimal places, the solution becomes more confusing. So I would represent all of them or convert them all into centimeters. Then the final answer, the focal length which I will receive, will also be in centimeters, which we can easily convert to meter in the last step. So let us find the focal length of the lens in air. Here again we have to use the lens maker's formula. What's that? 1/f. Here the focal length of the lens in air, so 1/FA is equal to refractive index of glass by refractive index of air. What is the refractive index of air? It's 1. So divided by 1 minus 1 times 1/R1 minus 1/R2. Here, in the first problem, I have explained that we have to use the, for convex lens, the first surface having radius of curvature positive, while the second surface having radius of curvature negative. Why? Because the ray of light after refraction goes through the side where there is the radius of curvature of the first surface. So we can consider it as positive. And the light that is after refraction go through a side, and the radius of curvature of the second side will be in the opposite direction. So we have the second surface having radius of curvature negative. And here let me write here what are the quantities given. R1 is equal to 0.2 meters. So R1 is equal to 0.2 meter, which I will take as 20 centimeter, and R2 is equal to 0.3 meters, which I will consider as 30 centimeter, and the refractive index of glass is given as 3/2, and the refractive index of water is given as 4/3. So let us substitute the values here, and 1/FA is equal to mu g, which is 3/2, divided by 1, so no need to write minus. In order to make the denominator same, I will write 1 as 2/2 and times 1/R1, so 1/20 minus 1/R2, so this is, minus sign is there for R2, so 1/-30. So this is equal to 1/2 times 1/20 plus 1/30. So here, in order to make the denominator same, I will multiply the numerator and denominator here with 3 and here with 2. So I will get it as equal to 1 by FA is equal to 1 by 2 times. If I multiply here with 3, so it will become 3 by 60 plus 2 by 60. So this is equal to 1 by 2 times 5 by 60, or this is equal to 5 by 2 times 60 is 120. So I have to find the focal length of the lens when it is in air. So I can take the reciprocal, which is 120 divided by 5. This is equal to 24 centimeter. Now if you want to convert this 24 centimeter to meter, it's easy. This is equal to 0.24 meters. So if you have a problem with finding 120 by 5, you can use a calculator. So you will get it as 24 centimeter. So I hope this is clear to you. It's similar to what we did before. What I did was I just converted the meters to centimeters, and I have also used the sign convention by which R1 will be positive and R2 will become negative. Then I use the lens maker's formula. I hope this is clear to you. Let us solve the B part. Will there be any variation of focal length in water? Analyze mathematically. So we know that the focal length of lens in air is 0.24 meters. Now let us find what will be the focal length of this lens when it is kept in water. So I write all this part, the data which is given will not be removed now, because we will use that for solving the B part as well. And just note it down somewhere. I'll note it here that the focal length of the lens in air was equal to 0.24 meter. Okay. So again, using lens maker's formula, we have 1 by FW is equal to refractive index of glass, because the lens is made of glass, divided by refractive index of water. Now the medium surrounding the lens is water. So mu W minus 1 times 1 by R1 minus 1 by R2. So this is equal to refractive index of glass is 3 by 2. 3 by 2 divided by 4 by 3. So I am going to multiply it by 3 by 4 minus 1 times, do you remember what was this quantity? 1 by 20 minus of 1 by minus 1 by 30, minus of 1 by minus 30. So here we have this equal to 3 times 3 is 9 by 2 times 4, 8 minus 1, let me write it as 8 by 8, so that the denominator is same, times 1 by 20, I multiply on both sides with 3, so it will become 3 by 60 plus minus times minus will become plus, then multiply both sides, both the numerator and denominator with 2, so 2 by 60, and we will get it as equal to 1 by FW is equal to 1 by 8 times here 5 by 60. So this is equal to 5 divided by 8 times 6 is 48. So 480. So the refractive index of water of the lens when it is kept in water, the focal length of lens when it is kept in water is given by 480 divided by 5, which is equal to, I have done the calculation here, it's equal to 96 centimeter. You can solve using your calculator. So we got the focal length of the lens when it is kept in water is 96 centimeter. So if you want to express it as meters, it will be 0.96 meter. So what happens to the focal length of the lens when it is immersed in water? It will increase, as we saw in the previous problem. So I hope this is also clear to you. I always recommend you to convert into centimeter only for such problems. Usually in physics we use the SI unit, which is meters, but here it will be easier if we consider centimeter, and doesn't matter even if the focal length is expressed in centimeters. Most of the time it is done so, but the final result, if you want it in SI unit, convert it to meters. So that's all about this problem. Now let's see the last problem. The fourth and the last problem, which is 6.24, states that the angle of minimum deviation of an equilateral glass prism was found in the laboratory 30 degrees. Afterwards, immersing the prism into water, the minimum angle of deviation was determined again. Find the angle of refraction at first phase of the prism at its minimum deviation position. Will the minimum angle of deviation change after immersing the prism in water? Refractive index of water is 4/3. So let's see here. This is a different concept from the problems which we solved earlier. This is related to refraction through a prism. And here we will have to use the formula for the refractive index of a prism in terms of the minimum deviation. Also, you should know the concept of minimum deviation. So let us see the first question, or A part. Find the angle of refraction at first phase of the prism at its minimum deviation position. So we have a equilateral triangle. What will be the angle of an equilateral triangle? Angle of an equilateral triangle will be 60 degrees. Now the refraction at the first phase of the prism. So suppose this is the normal at the first phase. This is the first phase. A ray of light is incident at an angle I. After refraction, it will bend towards the normal because it is entering a denser medium. So this is R1, and when it reaches here suppose this is the normal, and it will again emerge out, and this is R2, the angle of refraction at the second medium. And at the minimum deviation position, we know that the two refraction angles R1 will be equal to R2. And also we know that R1 plus R2 is equal to A. So from these concepts, we can say that R1 is equal to R2. So this is nothing but 2R1 is equal to A. Or R1 is equal to A divided by 2. That is 60 divided by 2, which is equal to 30 degrees. That gives us the answer for the A part. Find the angle of refraction at the first phase of the prism. So if this is the first phase of the prism, at its minimum deviation position, we know that R1 is equal to R2 for minimum deviation position. And R1 plus R2 is equal to A, which is 60 degrees because this is an equilateral prism, and we got R1 as 30 degrees. So that's A part. Now let us see the question B. For B part, we have to use the formula of a prism. In its minimum deviation position, we have to consider the refractive index. Now, they have mentioned that the refractive index of the prism will change when it is immersed in water. Just like lens, there will be difference when it gets immersed in water. When the prism gets immersed in water, its angle of minimum deviation also will change. So we have to find that angle of minimum deviation. and they have given us the refractive index of water. And let us see, we know that the refractive index is related to the angle of minimum deviation by the equation. Refractive index of the prism is equal to sine A plus delta m, where this is the angle of minimum deviation, divided by 2 divided by sine A by 2, where A is the angle of the prism and delta m is the angle of minimum deviation. Now, if the prism is kept in air, so this will be the refractive index of the glass of the prism with respect to air. And this is the angle of minimum deviation, which is given as 30 degree. So here, let us find what is the refractive index of the prism if it is kept in air. So refractive index of the prism when it is kept in air, if we find it out, we know the refractive index of water. So mu W is equal to 4 by 3, it is given. Now when it is immersed in water, instead of here, we will have to use the refractive index of glass with respect to water when it is immersed in water. So this is equal to refractive index of the glass with respect to air divided by refractive index of water with respect to air. So we already know the refractive index of water. We need to find the refractive index of glass with respect to air. In order to find the refractive index of glass with respect to water, then again we will use the similar equation where the angle of minimum deviation will be that when it is immersed in water. So the first step is to find the refractive index of glass with respect to air. So let us do that. This is equal to sine of A is 60 degree equilateral triangle plus. Here they have given the minimum deviation if the prism is in air is equal to 30 degrees. So 30 divided by 2 divided by sine A by 2. Sine A means 60 by 2. So this is equal to 30 plus 60 is 90. 90 by 2 is 45. So this is equal to sine 45 degree divided by sine 60 by 2 is 30 degree. So what is sine 45? It's 1 by root 2, right? So that is equal to 1 by root 2 divided by sine 30 is 1 by 2. So I can write the refractive index of glass with respect to air is equal to 1 by root 2. Instead of divided by, when I multiply, I have to take the reciprocal, which is 2. 2 by root 2 is equal to, again, root 2. Because 2 can be written as root 2 times root 2. So 1 root 2 gets cancelled. So we got the refractive index of glass with respect to air as equal to root 2. So let us keep it there. So we have found that the refractive index of glass with respect to air is equal to root 2. We will use that equation. Now we will consider that the prism is now taken from air and it is immersed in water. So the same equation when we consider the prism in water will become, let me keep the tester. So the same thing, same equation. The second case is, here we first use the equation when the prism was in air. Now the same equation when the prism is immersed in water, refractive index of the glass which is made of prism immersed in water will be equal to sine A plus, now the minimum deviation position or the angle of minimum deviation when it is kept in water. So let me express it with a prime, divided by 2 divided by sine A by 2. Our idea is to find this delta m prime, which is the angle of minimum deviation when the prism is immersed in water. So here we need mu g by mu w. So this is equal to mu g by mu w, or both with respect to air, is equal to sine A is 60 plus this one we don't know, so I am putting like this, divided by 2 whole divided by sine A by 2. A is 60, so 60 by 2 is 30, so we know this is sine 30. And mu g, we found it as root 2, so root 2, instead of refractive index of glass with respect to air, I will put it as mu root 2 divided by refractive index of water with respect to air. So I have to divide it with mu w with respect to air. So I will multiply with the reciprocal. So into 3 by 4 is equal to, now sine 60, this I have to write as such because I don't know the value of delta m prime. So sine 60 plus delta m prime divided by 2 whole divided by sine 30 which is equal to half. So half we will take to this side. So root 2 into 3 by 4, and when I multiply here with 2, so this will become root 2 times 3 by 4 into half is equal to sine 60 plus delta m prime by 2. Okay, so here you can find what is this value. You can use the calculator and find this value. The value is, let me just readjust, 2 and root 2 are here, so I will cancel it and I will write it as 3 divided by 4 root 2. So this is equal to sine of 60 plus delta m prime by 2. Now I don't have space here, so I will rub this part for further steps. So what is 60 plus delta m prime by 2 will become equal to sine inverse of this value, 3 by 4 root 2, or delta m prime will be equal to 2 times 60 plus delta m prime is equal to 2 times sine inverse of 3 by 4 root 2, and you will get this value as equal to 64.04 degree. So we have delta m prime. You can use the calculator to solve this. You will get this as equal to 32.02 times to 64.04. So delta m prime is equal to this value minus 60, which is equal to 4.04 degree. So what happened to the angle of minimum deviation when the prism is immersed in water? It reduced. It reduced from 30 degree to 4.04 degrees. So that is a large difference. So will the minimum angle of deviation change? Yes, it will change after immersing the prism in water. How is the change? It will decrease. So the angle of minimum deviation decreases when the prism is immersed in water. I hope this problem is clear to you, and if you have any